Right, this is Mr. Peterson with another screencast. This one is for Unit 3-1 in AP Environmental Science. Today, we're going to be learning about the climate and its effect on terrestrial biodiversity. This is a picture of a dust storm being blown off the western coast of Africa. It might be hard to believe, but that dust will later fall to the Earth on an entirely different continent, bringing minerals that will enrich the soil there. We won't spend too much time here talking about weather because biomes are determined not by any one weather event, like this storm working its way across the Midwest. Instead, we're concerned more with climate, which is like an average of all weather conditions. Usually climate is made up of the average weather over a period of 30 years or more. It's one reason why I can't stand it when people on a really cold day say, "So much for global warming." Now, we'll talk about global warming this year. It's really more accurate to call it global climate change. But for now, it's important to understand that one freak weather event isn't enough to say that the overall climate has changed. Climate is what we expect. Weather is what we get. Now, you might be thinking of how nice it would be to head down to the Gulf on an early fall day. You can feel the cool breeze, feel the warm water on your feet, all of those things that you expect to be there on an average fall day. Well, that's climate. It's the average condition. You can still roll down to Alligator Point this fall and get rained out at any given day. That's weather. Earth, under the moving air and water currents, creates a regular flow of wind and water. Because of the equator spinning faster than the poles, it creates a steady current we call the Coriolis effect. This is why air and water circulate in a given direction. This movement also helps determine wind patterns, which in turn drives different climates on Earth. Essentially, the equator is spinning faster than up by the poles. There are three main factors that drive weather and climate on Earth. One of these is the uneven heating of the Earth by the sun. Because most of the sun's radiation strikes the Earth near the equator, those regions receive the most heat year-round, whereas the polar areas receive less sunlight and are cooler. The change in temperature can lead to density differences, which drives winds. The temperature is a big part of weather, so areas that have cooler average temperatures are colder climates, while those that have higher average temperatures are warmer climates. Heat moves from warmer areas to cooler areas. This movement creates much of the winds and ocean currents on a global scale. For us, we're located in the zone of the westerlies, which means that most of the time, remember this is climate, the wind is usually blowing somewhere from the west toward the northeast. Most storm systems, especially in the winter, approach from the west. It's different all over the Earth, but the Earth's rotation sets up a regular direction to the flow of the air, and that affects the weather, which affects the climate of each area on Earth. Of incoming solar radiation, this is known as insolation, is at the equator and decreases as we move north or south in latitude. However, this is also affected by the tilt of the Earth. As the amount of incoming insolation increases, we can be moving toward summer. As it decreases, we move toward winter. And that's based off the tilt of the Earth as it rotates around the sun. In the northern hemisphere, in the summers, the Earth is tilted toward the sun. And in the winters, it's tilted away from the sun. Now imagine sailing across the ocean, relying on the wind to get around. You enter an area where the wind simply doesn't blow much. It's hot and humid. You could be stalled here for weeks waiting for enough wind to keep sailing. This is called the doldrums, and it's located at the equator. Here, the air is heated and rises straight up, cooling, causing condensation, and raining. But the wind, because it's directly over the equator, simply doesn't blow. The air just rises and falls, kind of like being in one spot. Just north and south of the equator is the movement of air. As air rises in the atmosphere, it cools, dropping moisture, then moves toward 30 degrees north or 30 degrees south latitude. Once it reaches there, it drops as dry air. This is why most of our deserts are located along this latitude. The air movement is called Hadley cells, and as you can see, it drops right around the tropics of Cancer and Capricorn. And generally speaking, many of our deserts are located at this 30 degrees north and south latitude. Here, you can see the movement of air between 0 and 30, 30 and 60, and 60 and 90 degrees latitude. This is where the winds will start moving in different directions. The mid-latitude cell will move up at 60 and back down at 30, bringing cool air again. You also have your wind patterns. The trade winds move west toward the equator. The westerlies move east toward the poles. And the polar easterlies are in the north latitudes move west towards 60 degrees. This solves some of the questions about why certain areas have the climate they do. This example I can give you is shown here. As you can see, where we live should be more desert-like in climate. Deserts also occur on the dry side of a mountain range because of the rain shadow effect, but more about that on the next slide. But because of our location near the Gulf of Mexico and the direction of wind bringing in moisture, we have enough rain for temperate deciduous forests. So, many different factors help drive climates. Now, I've already mentioned how large bodies of water can affect the climate of an area with the ocean, beach example. Some other large surface features of the Earth also play a role in modifying climate. For example, mountain ranges play a big role in determining climate. Mountains typically have great changes in elevation over short horizontal distances, and with increased elevation, the average temperature decreases. In addition, air that picks up moisture and is forced upward as it flows over a mountain cools as it rises. As it cools, water condenses and falls as precipitation. When it falls down the other side of the mountain, it warms up again, but contains little or no moisture. It's called a rain shadow. The Rocky Mountains have this effect. On the western side is California, which has an amazing amount of farms, grazing pasture, and more agriculture than you'd think. Just on the other side of the Rockies is desert, caused by the rising and cooling of air, dropping all of its moisture before it crosses the Rockies. Another example of the flow that moves heat around is the Gulf Stream. You can see in this image of the sea surface temperatures, red being hottest, blue or purple being the coldest. The warm ocean water from the tropics is flowing up past the southeast coast and across the Atlantic towards Europe. Most of Europe is actually the same latitude as the New England states or even parts of Canada. Like the southern end of France is along the same latitude as southern Maine here in the US. But it's much warmer in France due to this warm water trying to equalize by moving away from the tropics. As the water cools, by the time it reaches Europe, it sinks because it becomes denser as it cools and flows back to the tropics to repeat the cycle again. So again, that regular flow of heat through the moving water sets up regular patterns to the weather, which leads to an average climate for a particular area, like England, which is relatively mild compared to some of Earth's other latitudes across the globe. This warm current that pushes toward England that keeps this climate much warmer than other areas in that latitude. So just look at this map and where England is located compared to areas of Canada. For example, England temperature never drops very far below zero in winter, but in Canada, many parts reach negative 40 degrees. The main reason is the currents and England's closeness to the warm ocean currents moving north. Next up is the phenomenon known as El Nino and La Nina. These two events can cause global changes to rainfall, wind, and ocean circulation patterns. During El Nino, warm surface currents are blown toward Central America. This brings with it warmer air and therefore more rain. However, the Pacific Islands on the other side of the El Nino usually experiences a little cooler weather and much less rain than normal. However, during La Nina, the warm currents are now being pushed toward the Pacific Islands where they are now bringing more rain, when the other side, Central America, is actually receiving much less rain than normal. According to NOAA's Climate Prediction Center, during La Nina, a variable Pacific jet stream in association with a polar jet stream, seen here, shifted further south favors more normal precipitation across southern U.S., with below normal temperatures across the northern U.S. During El Nino, a strong and amplified Pacific jet stream extending across the southern U.S. is associated with a polar jet stream shifted further north into Canada, which favors above normal precipitation across the southern U.S. and above normal temperatures over the northern U.S. In these graphics here, average temperatures during this phenomenon over the many different recorded years that we've seen it occur through 2003, you can see that the temperature is higher in the north and lower in the south, the picture on the left. However, the amount of rainfall, pictured on the right, is higher in the south and much higher in California as well. Described earlier, here is the opposite phenomenon, where you can see the average temperature is lower in the north and higher in the south. However, the amount of rainfall is much lower in the south because of location to the ocean and geographical features that affect these two events, which then can vary the temperature and rainfall across the globe. Now for the last thing that affects the climate of an area. We've got to discuss the different properties of air, water, and land. To make this easy, I'm using a picture I took in Barcelona to illustrate this. Now, there's air, water, and land in this picture, along with my wife and kids playing in the beach. Air heats up rapidly in the sun, and it cools off rapidly when the sun goes down. Land changes temperatures a bit slower than air does, but water is the slowest of all. Imagine rolling down to the Gulf Coast during the fall. There might be days where the air has gotten cold, but the water would still be quite warm. A pool in your backyard may be doing the same thing. It takes water longer to cool off than it does for air. That difference actually insulates us here in South Georgia because the warmth of the Gulf water keeps our air warmer than it would be if we were more inland. The opposite is true in the spring. When the air warms up the first few times in early March, I doubt you'd put a toe in the water at, let's say, the beach or even in your backyard in a swimming pool, because the water hasn't quite heated up yet. Water is slow to change temperatures, and it helps moderate the climates of an area because it prevents temperature extremes. Go to the desert, the biome that usually lacks water, and the daytime temperatures can be well over 100, but the nighttime temperature can drop to below freezing, even in the summer. And that's because of the lack of water or humidity to buffer any temperature changes. Now moving on, another important idea of Earth's climate is the greenhouse effect. Gases like water vapor, carbon dioxide, methane, and nitrous oxide are called greenhouse gases because they allow visible light, UV, and shortwave infrared light to pass right through to hit the Earth's surface. They're just like the plastic panels that make up this greenhouse, used for growing strawberries in the winter. When the sun's light comes to the Earth, it passes right through the atmosphere and hits the Earth's surface, and it reflects. But the wavelength of the reflected energy is longer, which means it becomes less visible light and more infrared energy than it was on the way in. The greenhouse gases in the air don't block visible light at all, but they can absorb this outgoing infrared energy and reflect it back to the Earth, or simply hold it in the atmosphere to keep the Earth warm. Now, all of this is perfectly natural. The greenhouse effect is one critical factor that makes our planet different from the moon. No atmosphere on the moon equals no greenhouse effect equals wild swings in temperature from the light to the dark side. So the greenhouse effect is a good thing for Earth. Where the greenhouse effect gets to be an issue is with the humans enhancing the greenhouse effect. Many human activities release air pollution that contain greenhouse gases, and by adding more of these greenhouse gases to the atmosphere than Earth naturally remove, we risk making the greenhouse effect too effective and having the Earth's average temperature change over time. There's a tipping point idea in here somewhere. The parts of the Earth permanently covered by snow and ice reflect most of the light that strikes it because they're light in color. And they reflect that incoming light back out as visible light, not infrared. So, no warming. But if the Earth's temperature starts to change because of human activity, and those areas of snow and ice start to melt, then the darker rocks and water underneath won't reflect as well. They'll change that reflected light into heat, which warms the Earth more. In that way, a small change of a degree or two in the global temperature could lead to an even more drastic change in the long run, because a higher temperature would melt more ice, which could lead to more warming. And it's another example of positive feedback. I'm not sure this falls right into line with the chapter we're in, but because we're on it, cities have an impact on climate as well. All of the pavement and buildings in a city absorb heat during the day and release it back into the atmosphere. All of the cars, air conditioners, and other activities in urban areas release more heat. Plus, there's less natural cooling from water evaporating from trees. All of this results in higher temperatures around cities and urban areas, while more rural areas end up being noticeably cooler. It works even in the winter. If you live out in the country and you notice frost on the ground, as you drive into the city, you might see a sudden stop to the frost. That's all around. On a cold night in Thomas County, it may hit 27 degrees out in the rural areas, while Thomasville itself never gets below 32. This whole idea is called urban heat island, and it just means the cities usually have a higher average temperature than natural areas around it, which can lead to more evaporation, more cooling, and then more rainfall downwind of cities. For the first half of 3-1, thanks for watching.